This program looks at the electrophilic addition of alkenes. An addition reaction is where an electrophile adds to a molecule with an electron-rich site. Let's look at a few of these terms. First of all, an electrophile. I think of that as a negative liking substance because electrons are negative, that accepts a pair of electrons. Well, positive things would be electron liking. So these are examples of electrophiles, the hydronium ion, nitronium ion, which we'll learn a little bit more about later on, and the methyl cation, to name but a few. But also neutral compounds, particularly neutral compounds that have permanent dipoles or induced dipoles, can also accept pairs of electrons. So here we have a couple of examples, hydrogen bromide and water, which have permanent dipoles. We can induce a dipole, however, in a halogen. So if I bring a negative object near this bromine, the electrons would be repelled and move to the left side of the bromine molecule, leaving the right side slightly positive. So these also can act as electrophiles. And it adds to a molecule with an electron-rich site. Well, if we consider the following molecule shown here, we have a particularly rich electron environment where we have the double bond. So we're looking at electrophiles moving to this region. We need to be able to understand the mechanism by which it happens. So I'm going to start off with ethene and bromine. As the bromine approaches the double bond site, electrons are repelled to the far end of the bromine molecule. As a result, it becomes temporarily polar. Those electrons that are present in the double bond form a new bond with the bromine. I'm using a double-headed arrow here to indicate the movement of two electrons. Simultaneously, the bond between the bromine and the bromine, the two electrons there move to the slightly negative end of the bromine molecule. We then create what's called a carbo-cation, a species that has a positive charged carbon in it and a negative bromine. So that occurs in the first step. In our second step, we're going to take our carbo-cation, which has a positive charge, and the bromine, which has a negative charge, and they will be attracted to each other. Again, using a double-headed arrow to show a movement of a pair of electrons to that positively charged carbon. And here is the resulting molecule. Here's a look at the overall reaction. So I'll just summarize the steps here and we'll go through them. The approaching nucleophile is attracted to the electron-rich double bond. The slightly positive pole of the induced dipole attracts two electrons from the double bond and forms a carbon-bromine bond. Simultaneously, the bromine undergoes heterolytic fission, with two electrons from the bromine-bromine bond moving to the slightly negative bromine. The carbon not involved now has a positive charge because it's lost an electron and forms a carbo-cation. Lastly, our bromine ion bonds with the carbo-cation. So that's a quick summary of the steps involved in this reaction. Let's look at another one. Again, ethene, and this time hydrogen bromide. Hydrogen bromide is a permanent dipole, so it will orient itself in the following fashion. And in a similar fashion, the double bond will break with two electrons forming a bond with the hydrogen, and then heterolytic fission, causing the formation of a bromine ion. There we've identified our positively charged carbo-cation, which now attracts a pair of electrons from the bromine. And we finish up with the following product, bromoethane. Now I'm going to make a slight change to this. This time I'm going to bring propene nearby. And again, I'm still going to use the hydrogen bromide. And again, we're going to start off with our first step. The double bond breaks and a new bond forms with the hydrogen. Now this case, we have a choice. Which carbon will it go to? Because it makes a difference. In our previous case, it didn't make a difference because our molecule was symmetrical. But here it does. Will the carbo-cation form on the terminal carbon, where the hydrogen bonded to the central carbon? Or will that hydrogen bond to the end of the molecule following a carbo-cation in the center? To resolve this, we have to employ the following idea. The species with the more stable carbo-cation is favored. So again, we're going to identify our carbo-cations. And in terms of favoring, the tertiary one is more stable. the secondary next, and the primary the least stable. So in the top molecule, I have a primary carbocation. The lower diagram has a secondary carbocation, so that is going to be more stable. That's my favorite configuration. There is a second way to arrive at this. Some of you might have heard of something called Markovnikov's rule, where we say the rich gets richer. The currency here is hydrogens. If we go back to our original molecule, we can see that we have 2 hydrogens on the terminal carbon, and we have 1 hydrogen on the one in the middle. Markovnikov would believe that the hydrogen should go to the hydrogen that already has the most. The hydrogen would be preferred on the terminal carbon, which indeed it was. Now, the Markovnikov rule is a tool to drawing these. It's not a reason. What I've shown in red is the reason. A secondary carbocation is more stable than a primary carbocation. So now we can bring in our bromine, which will attach to the carbon in the middle, and we finish up, in this case, with 2-bromo-propane. And here, the overall reaction. Let's try a question involving these ideas. Which of the following condensed formula represents the major product between propene and water? So there's my propene molecule, and there comes water nearby. I'm showing the slightly positive hydrogen being closer to the double bond, because that's the one that will form. So the double bond breaks open and bonds with that hydrogen, and then the hydrogen-oxygen breaks by heterolytic fission, creating an OH ion. Which will be our favorite configuration? If we employ Markovnikov's rule, there's 2 hydrogens on the end, 1 in the middle. The hydrogen would prefer to bond with the one at the end. And then the OH will connect in the middle. So our final molecule will look something like this. And that one we can identify by a quick glance as A or C. But a quick counting of the number of bonds of the second carbon, we can see that there's too many in C, so A will turn out to be our answer. Please let me know if you found this useful by adding a comment or giving us a like.